I'm Leonardo Rolla. I'll talk about the contact process with modified border. This is a joint work with Enrique Angeli. The model we consider is a modification of the standard contact process in one dimension on the integer line. We represent a configuration as a subset of z, which is of course the same as a function from z to 0, 1. And the modification is only that the rightmost site, if there is one, will infect the neighbor to its right at the rate that we call lambda e, where e stands for exterior, which is possibly different from the rate lambda I, where I stands for interior, at which sites in the interior of this interval will infect other sites. This is a non-local dynamics. So even if we use a graphical construction such as Herrick's graphical construction, we have to be careful when we talk about existence of paths. For background on this model, you refer to the article by Duret and Chinazzi. So we say that this process percolates if any non-empty infection has positive probability of surviving, and the classical model is when lambda I and lambda E are both equal, which we call lambda, and the reference for the classical model would be Liggett's book. And when both are equal and we call them lambda, there exists a critical lambda which is strictly larger than 1 and which is finite, such that the system percolates for higher values and does not percolate for smaller values. Now define lambda I star as the critical value of lambda I for a fixed lambda E. And the first question we're interested in is if lambda E is increased with respect to lambda C, it's strictly larger, will the critical value for lambda I be strictly smaller than lambda C? And conversely, if we take a subcritical lambda E, does the critical value for lambda I increase strictly? The answer is negative to the first question, given by Duret and Chinazzi in 2000, and positive for the second question, given by Enrique Angeli and myself. It should be emphasized that questions in the spirit of enhancement are usually much harder for oriented models than for non-oriented models. And here is a good example. Just by embedding a graph into a graph of higher dimension, it immediately follows that the critical parameter lambda is non-increasing in the dimension. However, if we want to prove that it is strictly decreasing, that is still an open problem. We now look at the phase space, where we plot the two parameters, lambda I and lambda E, and the axis, and we consider how these models will compare with the classical model, which is the one on the diagonal. First, the model on the diagonal, it is additive and therefore attractive, and above the diagonal, when lambda E is higher, this model is not attractive and it's sub-additive. And below the diagonal, this model is attractive because it is super-additive. And now some trivial considerations, as just by comparing with the classical model, since we know that the classical model dies out at the critical density, then by reducing one of the two parameters, the model still dies out. And if we take both parameters larger than the critical value of the classical model, then just by comparing the rates of transitions, we have that in all this green region here, the process percolates. Moreover, by comparing with the case where lambda I is infinity, then the boundaries of this process are just performing simple random walks, and we see that this process will not percolate. Now, the results of Duret and Chinazzi are that in this region of the phase space, the process dies out, and in this region of the phase space, the process survives. And this implies that there is a critical curve here separating the parameters for which the model dies and parameters for which the model survives. And below the diagonal, since the model is attractive, it is monotone with respect to the parameters, and that implies existence of a curve, which we can think of as a continuation of this curve, that goes just up and to the left, that separates part where it percolates and the part where it dies out. And with these horizontal and vertical segments, which should not happen, the curve should rather look smooth like this. Now, the results by myself and Enrique Angel is in this region of the parameter space that's qualitative. It's just about existence of a region with this shape. There is no percolation, the system dies out, and on this critical curve here, above this, the main critical point, the process survives. Moreover, we show that the critical curve cannot have vertical segments. So the most pessimistic case, the curve will have a horizontal segment here, then decrease, another horizontal segment, and then decrease, and so on, and it will tend to infinity in a strictly decreasing way as lambda I goes to infinity. Then it's still a work in progress to rule out these horizontal segments here from the critical curve. Stating those results more formally, the two results by Darret and Shinasi are that first, if lambda I is subcritical, the process dies. And that means when lambda E is larger than lambda C, then this critical value of lambda I, which in principle was not so well defined because there's no monotonicity in that region of the phase space, it equals lambda C. And the second result is that when lambda E is larger than 1, strictly larger than 1, we can always pick lambda I large enough so that the system percolates. The results by Enrique Angel and myself are the following. First, this function that for each lambda E gives the critical value of lambda I, this function is strictly decreasing on this interval. And as a corollary, if we take lambda E strictly smaller than lambda C, no matter how smaller, this will cause the critical value for lambda I to increase strictly. Second, for all values of lambda I, we have the critical lambda E that is defined analogously will be strictly larger than 1. Finally, we show that when lambda I equals lambda C, we take internally the critical value and we increase the external parameter by some amount, doesn't matter how tiny that amount is, the process will percolate. And we should remark that this is in contrast with the conjecture that if we help the system by increasing lambda on a finite region or even on a fixed site, then this process should still die. And another remark is that in this regime here, the process, it percolates, but still it does not have any non-trivial invariant measures. We conclude with some fragments of the proofs. First is the observation that when lambda I is at least as large as lambda E, the process is superadditive, hence attractive. Then from a straightforward adaptation of known arguments, we get that the speed is well defined, that's the speed when we start with all sides to the left infected and all sides to the right vacant. And the same speed actually works for any semi-infinite initial configuration. Then finally, we go to a lemma where the process seen from the edge, so it has a configuration which is infinite to the left and finite to the right. Seen from the rightmost occupied site, it converges to a unique measure. And now the juicy part of the proof. First, this proposition. If a pair of lambda I and lambda E percolate, and if we increase lambda E a little bit so that it's still smaller than lambda I, then the speed increases by at least the same amount. And finally, when in this regime, when lambda E is subcritical, then taking lambda I to be the critical lambda I for that value of lambda E, the speed will be 0. The last theorem follows the same line of argument as the classical model that you see on Liggett's book. So we have a block argument where we have paths in quotation marks that meet in the plane. So here we really need this model to be 1 plus 1 dimensional, and then we can dominate it by an oriented percolation model which has finite range of dependence. Except that we cannot really talk about paths here. So when we make this picture, we have these little branches, and these branches, they are an integral part of the path because they are here to ensure that between leftmost and rightmost occupied sites, we infect at rate lambda I. And in order to get these blocks, we just have one long strip of a certain type of path crossed several times by another type of path so that they protect each other. And thank you for watching.